Hello everyone, welcome to tonight's live stream where we're going to be looking at a bunch of other stuff. I was wondering why I didn't see any pogging emojis going on today, but have a look. With the new setup, you can now actually see things that are going on. Look, we can see the emojis. Oh, how amazing is all this? Yeah, thank you. I did spend an embarrassing amount of time sorting that out with the graphics this time. Uh, Yeah, well, I'm glad you are, because tonight we are going to be going through all the mathsy stuff. So prepare yourself. And I've also got a very funky camera angle to show you, which I'm reasonably proud of, but we'll see how it looks. I've got my iPad just in case it all goes absolutely terribly. But tonight we are going to look once again at logic gates. We're going to look at boolean simplification. If you wonder what I'm doing, I'm struggling to plug my iPad into the actual cable, which is just give me a second. Let me lean over and maybe I can do it. There we are. Done it. Sorry. Live stream is a bit embarrassing when you can't actually plug a cable into an iPad. But after that, we'll have a look at floating point normalization, a bit of binary to hex or hex to binary in addition, and we'll go from there. But first thing I want to start with tonight was looking at this. That's my iPad. We'll look at that. This is a truth table, as we know, and it's got the basic logic gates in it. Your question might differ a little bit to this, but certainly we are going to be looking at this in a broadly similar way. And the idea is we need to know about a bunch of logic gates that you've studied before. And I think the important thing is just recap on the logic gates. You've got your NOT gate, which is illustrated by a little line above something. In fact, let's cut to the cool secondary cam. Look at this, look. I can actually write, it'd be cool. So a NOT gate would be a letter with a line above it, and hopefully that's legible to you. Now, this only gives us the inverse. So if 1 goes in, we get a 0 coming out, and if 0 goes in, we get a 1 coming out. We've also got our AND gate, A dot B. Remember, that's really important. It's the dot there, because we are dealing with different symbols, and we get 2 inputs here, A and B. And remember, the truth table looks a bit like this. And an AND gate, we only get a 1 out of it if they're both turned on. So it's only in this instance. Everything else is a 0. We've also got our bad boy, the OR gate, and this is where it's very cleverly illustrated by a plus symbol. So A or B. Now again, if we draw the truth table out, and hopefully I'll draw it a bit bigger this time so you can see what's going on. What we're looking at there with an OR gate is if either of them are turned on, we can give it a 1. So these are both off. So I'll put a 0 in here. One of them's on. One of them's on. Now, in this case, one of them is on. In fact, both of them are on. But for an OR gate, that doesn't matter. We get a 1 out of it. The last one, the cool one, is the XOR gate, or some of you have been saying the XOR gate. XOR sounds like some sort of alien prince. But anyway, that's it's almost like a sideways X-Men symbol, if I could draw a little bit better than that. But what you get from here with your bog standard 2-input truth table is we only get it turned on if only one of them's on. So it's off there, one of them's on, one of them's on. And the interesting bit about XOR is that because both of them are turned on, we get a big fat 0 there. And that's what we're looking at really in terms of the basics of the logic gates. Now, with the question that we've got here on the board, again, I need to remember that that's the iPad input. With this question on the board, what we're really looking at is talking about what's going here, because we're going to go down a column at the time and fill it in. Now, hopefully, I can, without making too much of a fool of myself, find a way to get this working, because there should be an annotate tool that I can work on with. And he says, no, there's no annotate tool in full screen mode, apparently. But never mind, because what we can do is we can work it out and go through it. So we'd go down this one and look for A or B. So remember, in either case, we're looking for one of those to be on. So I'm going to flip over to my beautiful new screen, and we'll put some stuff down in there. So we're looking at A, B, A or B, A and B. Move my little Funko at the way there. A XOR B, and then A or not B, which is fine. Okay, so let's work that out. We've got 0, 0, 0, 1, 1, 0, 1, 1. First of all, A or B. Either of these need to be turned on. Straightforward. A and B. Both of these need to be turned on. And you could pretty much learn these truth tables if you don't get it working. Now, unfortunately, I don't have enough followers to get a donation link yet, but there we go. Thank you very much for your enthusiasm. A, X, or B, we're talking about the exclusive OR. So no, yes, yes, no. Remember the difference between the OR and the exclusive OR is just that last state there. And this one, A or not B. So in this case, it's a very different one. This is one of the earliest mark schemes we've got for this question. And it's a little bit different to the ones we've seen before, because normally we're building up from part to part. So what I want to do here is we're saying we're looking for A or not B. So in this case, really, we should have a not B column. So let's make a not B column. And I'm doing that by doing a not B. And a not B is the opposite to B, isn't it? 1, 0, 1, 0. So now that is this column. That is this column here. And I'm ORing it. So I'm just going between these two. One of them is on, none of them are on. One of them is on, one of them is on. And there's your final piece of work, worked out reasonably easily there. So what I'd like to show you next is going on to the basics of normalization. Now, let me pop that up here because that's quite important here. So topics for Thursday's test are going to be all the mathsy stuff. So you're doing your logic gates, you're doing your boolean normalization. Then we're doing hexadecimal, binary, and addition. And then you're doing a floating point normalization. Now, it's a bit of an odd question. It's the oddest question I've ever seen. So we'll have to think about how floating point numbers work when we get to that part of the lesson tonight. But it's all reasonably straightforward. It's applying the knowledge you've already got. And you've all shown me you're really pretty good at that. And of course, a certain member of the class who likes breakfast very much and also will remain nameless is like some sort of machine at doing these floating point normalizations. So we'll see. On Friday then, there's a few different pieces. I can't remember the top of my head what that is, but if you have a look at the link for the live stream for tomorrow, I've already got all the titles and stuff in there. But tomorrow's live stream will be at 9 o'clock, not 8 o'clock, because I know that more people prefer the 9 o'clock slot. And also, it's a Thursday, so it gives me a chance to put the bins out because I'm an old man and have to put the bins out. That's my life. It's so much fun. It's honestly brilliant. Anyway, let's have a look at a floating point normalization question because we should be able to track one down reasonably easily. So let's pop over here and let's see if we can track one down. So here we go. This is the Wales 2018 paper, and there's a good bunch of stuff there for this normalization question. Now it's 8 marks long. So that means that there should be at least 8 steps involved in it, but we'll see how we go there tonight. And the other thing we need to think about is this. Now, this is my ultimate cheat sheet. And hopefully you remember that things like the commutative laws, the associative laws, and the distributive laws, things like that, can be largely ignored if you treat this as if it was simple maths. And we're talking about like expansion of brackets, factorization, things like that. If you treat it as simple maths and then apply the basic and and or rules when you get to those sort of states, you can avoid having to learn loads and loads and loads of stuff. Also, I'm just going to put, it takes me an hour to put a bin out. Well, you know, we live in the 21st century, everyone. Recycling. There are multiple bags, multiple things need to be put out. You've got to check, double check, make sure it's all okay. Maybe I just care more than most people. Oh, well, there we go. 1 second, sorry. To do an old man cough then. So I didn't want you broadcasting to everyone's living rooms. So let's have a look at this question. Let's work through it together and let's see if we can remember how to apply it. If you want to do more than one, we can, of course, do that. So let me copy that down. We've got A and not A or B or C, sorry, not C, and A or B. And this is where it becomes important that you know the difference between your ands and your ors in Boolean simplification. Not B or C, or not B and B. So let's cut to the core cam. And you see the very first thing that we look at is we look at that expression and we say, is there anything that we can immediately get rid of? And hopefully you're thinking, that one might be a good one there, which is very difficult to see because my face is over the top of it. But that one there, B and not B, that is part of the basic rule structure. Now, if we go back to our cheat sheet, you'll see that anything and the inverse of itself becomes 0. And if you have a look over here, anything or 0 is just itself. So by applying both those rules to that, what that basically means is that this disappears. So we rewrite it underneath like this. Now ignoring this part because it's just disappeared. Not B and itself just disappears and doesn't really become anything. So at this point then, you might be looking at it and going, well, I don't know where we go next. Now, this is the point at where you want to expand those brackets. Treat it like a basic mathematical formula. It's algebra, isn't it? Treat it like an algebraic expression and factorize it out. So that means we need to multiply out this bracket. So it's A and not A, or A and B, or not C and A, or not C and B, or A and not B, or A and C. Now, if you remember what I said to you the other day, one of the nice things about this is that elements that with an and are pretty much glued together. They are sort of chunks, and the ors allow the chunks to float around. So we can move these chunks around the ors, but they have to stay together. But within that, we can actually flip the terms around. Now, what you might do is look at this and go, where's there a common factor that I can factorize out? And hopefully that will result in some more normalization. And from this one, there's lots of A's. Now, again, here, do remember, please, that at this point in our understanding, we need to treat B and not B as different terms. Although it is possible to factorize out B from both of those, it's not in your spec, and it's far more complicated than we need to deal with. So look for something obvious, and I think A is the most common factor in here. So my first job is to rewrite it with the A's as the first symbol. Now this one I can rearrange to be A and not C. They're identical symbols. I'm going to skip this one for now because I want all my A's together. And I'm going to bring this one in, not C and B. And I'm going to take this, and I'm going to factorize out the A. So this becomes A and, big load of brackets. First one, of course, is A and, well, actually, I tell a lie. Let's think about this one before we go, because I've been talking and talking, but there's a term there that can be disappeared to nothing. And in fact, yes, just as I noticed it, you guys noticed it too. You are absolutely right. A and not A can be removed from here because that is a null term that disappears. So we can ignore that if we want. And we'll start here. So A and B, or not C, or not B, or C. And of course, that on the end. Now, we can rearrange that if we want, but I think you're able to see there we've got B or not B, and C, and so not C or C. So that bracket ends up, if we have a look at our cheat sheet for our rules there, anything and not itself becomes 0. So we go back to the right camera there. So that means we're getting B and not B becomes 0 or 0. Now, 0 or 0, that's a repeated term, so we can get rid of that. A and 0, or not C and B. Now, there is a rule for A and 0, which we can go back to our cheat sheet and have a look at. A and 0 just becomes 0, so we can get rid of that. A and 0 becomes 0. And hopefully remember that the 0 term can just disappear. Again, have a look at the cheat sheet. A or 0 just becomes A. Now, in our expression here, we've got this is A and this is 0, so it just becomes not C and B. And ta-da, we've simplified it as far as we could go. And it's just a broadly simple process there. We've got a question here. Would it not be 1? Let's have a look. So A and 0. If we have a look at the cheat sheet here, A and 0 is up here, look. Okay, so A and 0 becomes 0. It would only become 1 if it was A or 1 over here. And I don't think we've got that in there. So let's have a look. And of course, we do have people saying, is it not this, is not that? Why don't we have a look at the mark scheme and see if I've gone wrong? Because chances are I have. Let's have a quick look. Now that should be 2018 Wales. So let's have a look at the 2018 mark scheme. The problem is the more you do this, the more you confuse it with other things. So potentially I've got this wrong. Let's have a look. The stakes are high for me. Does my entire representation rest on this being right? We'll see. So that's question 4. Lovely. Right. So let's go through to question 4. Oh, dear me. Stop flipping over, computer. Right. Okay. So next one. Next one. Question 4. Well, unless I've got completely the wrong one, they've gone a completely different route to me, haven't they? So they've got A and B, not C. So where have I done wonky? I have gone wonky here, haven't I? So I've got the multiplied out there, and I think you're right. I think I've applied the wrong rule. So yeah, well done. Yeah. So let's backtrack to where I went wrong. So if we backtrack to here, what I've done is I got excited here and applied the wrong rule, didn't I? So this is why it's important. Again, you know, how many years have I been doing this? Well, count the amount of hairs on my head. There's not that many. So I've been doing it quite a while. But if we go back to the cheat sheet here, and we're looking for A or not A is 1. You are absolutely right there. And that's where I went wrong, because I got excited with B and not B becoming 0. But actually, B and not B becomes 1 or 1, which is absolutely right. So thanks for pointing that out. We'll do another one in a minute. You wouldn't think this is exactly the same one that I did with you in class the other day and got in 1, would you? No. Stay cool, Mr. Morgan. Stay cool. You know what you're doing. So now we've got a replicated term. So we go A and 1, which we don't need the brackets for, or C dot B. And if we look at the cheat sheet, we should see that A and 1 just becomes A. So we can simplify that one down to A or not C and B. You are right. Absolutely. So apologies for that one going a bit wonky. Let's do another one just to prove, at least to myself, that I'm not a complete moron and I sort of know what I'm doing. Because whilst these are reasonably straightforward to do, I say reasonably straightforward, it's easy to make mistakes with all of this stuff. And as I said to you a million times when you're doing binary, it makes sense to write down little cheat sheets to yourself on the side of the paper, because otherwise what you're left with is a situation where you are just sort of writing things down and hoping for the best and making silly mistakes because you're confident in your answers, as I was there. I've done this stuff so many times and it's still quite easy to get wrong. So if I can get one of these papers to actually load, I'll be very, very happy, because I'm having a bit of a go. Oh, here we go. Here we go. Right. So let's have a look at one here. And we'll pop this into full screen. And we'll have a look in here for, this is the English paper the same year. And you remember that it's not to a certain member of the class. When I say English paper, I don't just mean any random English exam board. I mean the WJEC paper for England. Right, there we go. Just clarify that, because we don't want to get too confused, do we? And have I missed the question, or is it later in the paper? It could be. Let's have a look. Keep going. There it is. So it's number 10 over here, look. And it's broadly the same sort of idea, isn't it? But remember, the English example, they like using P, Q, and R. We like using A, B, and C, which is quite nice. So let me copy that out. P and not Q or R, or Q and P, or not Q or R, and P or R, or not S and S. So how are we going to do this one then? Well, hopefully right this time. That's my first thought. So first of all, look for a term that can be removed. We've got our not S and S, which again disappears, becomes nothing. So rewrite the entire term. And if you've looked at the mark schemes for these questions, you'll know that the mark scheme is written in such a way as to simply be a bunch of the lines. It doesn't really give you a massive amount of detail what's happening from line to line. So it is important to rewrite it because I'll be looking for the changes as you go. So at this point, then, there's nothing obvious that's going to go on. So let's expand the brackets. P and not Q, or P and R. That's a very big dot there. Sorry about that. Or Q and P, or Q and not Q. I'll have that later. Or R and P, or R and R. I'd like to do something with that as well. So the two terms I pointed out there, the first one, Q and not Q, that disappears because that cancels each other out. And here we've got R and R repetition there, so we can simplify that to one element. So it's going to be P and Q, or P and R, or Q and P, that disappears, or R and P, or R and R becomes R. Once again, are there two similar terms there? Well, P and R and P, remember we can just flip those around. Those are both the same term, repetition, so we can remove that. P and Q, or P and R. I need one of these now, or Q and P, or R. Oh, what's this? Looks good to me. Repetition of terms again, P and Q and P. So that means I need one of those, P and Q, or P and R, or R. Now, you might go, well, what term am I going to take out of here? Well, the first one I would probably try and take out is I'd try and take out P, because something interesting might happen here. So let's try and take out P and see what happens. Now, at this point, right, hold on. Have I done it wrong? Have I copied it down wrong? Because once again, somebody's pointing something out. Was it P, not Q in line 3? Let's have a look. So line 3, we've got, oh, yeah, there we are. There's a good job you're here, guys. So that's not a repeated term. That is a different term. And again, this is the difference between me doing it first thing in the morning with you and doing it 8 o'clock at night. My brain ain't working quite as well. So why you got to get lots of sleep is very important. That's my PSA for all teenagers everywhere. So bringing that element down then, that is not a repeated thing now. So we've got P and not Q, or P and R, or I'm going to put P at the front there, P and Q, or R. Now we've got 3 P's, so it's a bit more obvious which ones I'm going to jump together now. So let's factorize that out. P and not Q, or R, or Q, and R. Yeah. No, don't use me as the example. No, please don't. So at this point, then, we need to simplify that. Now, not Q or Q. If we remember our cheat sheet this time and don't just go, Mr. Morgan, taking a good old guess at what it might be, we'll hopefully come up with something good. So Q or not Q, which is over here, which comes as 1. So back to our paper. So that means P and 1, or R. That's R. Now, there's got to be a rule for that in our cheat sheet, so let's go and have a look. A or 1 is just 1. So that entire bracket boils down to being that. Which means then that what we should be doing is looking at a rule for P and 1. So again, let's have a look. P and 1 is just P. So if we go back, that gives us P or R. It's boiled down quite simply. Now, again, you see me do 2. You see me make embarrassing mistakes in both cases. I'll just say, at least the second one, I didn't have to rewrite at least half of it. It was only one symbol that I got a bit wrong on. But you can make mistakes very easily on this. No matter how many years you've been doing it, no matter how confident you're doing with that, you can make mistakes with it. So the best thing to do, and I honestly think this, is to try and remember the and the or rules. If you're going to rote learn anything, rote learn the and the or rules. You know, at the very least, what you should be aiming to do is rote learn those, or at least remember them at the start of the exam. And the moment I say go, the moment I say start, turn the exam over and write down the and or rules on the margin of the first page. That way, it's going to be the most accurate it can be. Absolutely the most accurate it can be. And then when you get to that question, you flip back. Got another question here. So when we do our answers in the test, should we do another line for every change we make, or can we do multiple changes on one line? It depends how far ahead you're going. If they are simple changes, like an A and a not A, and maybe a B and a 1 or something that are going to be simple and obvious what's happening, that's great. What I would suggest you do, though, is why not do like me, is when you are identifying symbols that you're going to do something about, just put a little underline under them. Yeah, make it obvious to me what's going to happen, and it'll be more easy, much easier for me to give you the marks in that. But please do try and memorize this little bit. Everything else is application of maths that you've done before, so you don't need to panic too much about that. But this stuff here is really stuff that you should be trying to remember as best as possible. Okay. With that done, then let's have a look at some hex and some binary and all that sort of good stuff, because one of the things you're going to have to do in your assessment, of course, is you are going to have to do the standard sort of question where you convert some numbers, you sort of do a bit of addition, and all the reason they do that, in one go, is because the assessment really is trying to look at multiple conversions in one, and one of the nice things that WJEC do, at least, is they don't put every question in for the sake of it. They are very much open to the fact that if they ask you once and you know what you're doing and you can apply it as much as possible, then they're happy to give you the marks. And I'm just going to show you this question here. And I'm going to zoom in over here, hopefully. This is the sort of thing that really you should be pretty good at. This is the sort of thing they like doing. It's converting two hexadecimal numbers into binary numbers and then adding them together. Now, just a reminder, I'll put these down on my paper as we go here. That little 16 illustrates that it is a hexadecimal number, because 31 in hex could be 31 in denary, but 31 in hex and 31 in denary have very, very different values. Okay, so let's go in and see how we do that, because it's reasonably straightforward. First of all, I've got to stop pressing that button. I'm going to take that and just unplug that one from it. Each of these numbers is a 2-bit hexadecimal value, which means that we can easily transpose them and change them. Okay, 3, 1, if we treat it as two separate values, 3 and 1, we'd need to write down 2 nibbles. So our first nibble for the number 3, you remember the values of 1, 2, 4, and 8, because they are the place values. 3 is represented by a 2 and a 1. 1 then, in a nibble, and remember the reason it's called a nibble is because it's half a byte, and computer scientists are comedy geniuses. A 1 is just represented like that. And what we do is we combine that together to make the final number. It's reasonably straightforward like that. Let's do the 6D. So we treat the 6 and the D separately. So 6 is comprised of a 4 and a 2. And D, well, what number is that? Well, if you remember, one of the things I encourage you to do is just do A, B, C, D, E, F in a margin somewhere, remembering that A is 10, where you can work out what everything else is. And that is easier to refer to than trying to remember. You know, I've told you the story about the mistakes I've made with that, where I've very easily just transposed the numbers in my head. Now, D is 13, so that means I must represent 13 in a nibble. 1, 2, 3, 4. So 13 is going to be 8 and 4, which is 12, and 1, which is 13. So now I need to add those together. So I need to write these numbers as if they were an entire thing. So 0, 0, 1, 1, 0, 0, 0, 1, plus 0, 1, 1, 0, 1, 1, 0, 1. And it's at this point that it's worth writing down the binary addition cheat sheet. And that is remembering these numbers. What do those numbers look like in binary? Well, 0 is 0. 1 is 1. Very straightforward. 2 is 1, 0. And 3 is 1, 1. That's a little bit more easy to forget. And then we're just going to do a bog standard primary school addition where we've only got ones and zeros, and the maximum number any single place can be is 1, 1, or 3. So we start on the right-hand side here, and we say, what is 1 plus 1? Well, it's 2. 2 is 1, 0, which means we put down the 0 and we carry the 1. Next place, 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1, well, that's 2 again, isn't it? So that's 1, 0. So we do 0, carry the 1. 0 plus 1 is going to be 2 again. So it's 0, carry the 1. And 0, 0, and 1 is 1. And there, very simply, we've got a working binary addition. Now, thankfully, I don't think I've gone wrong when I did that. So there's a first time for everything, isn't there? Well done, Mr. Morgan. Go and give myself a nice cup of tea to make sure that I reward myself for that tonight. But you remember that there is a type of binary addition that leads to problems as well. So let's have a look at that. I'm just going to go crazy with it and go 1, 1, 1, 1, 1, 1, 1, 1 plus. Well, let's just do the really comedy version. 0, 0, 0, 0, 0, 0, 0, 1. Now that is going to cause an error for us. So let's start on this side. 1 plus 1 is 2. So that's 0, carry the 1. 1 plus 0 plus 1 is 2. 1 plus 0 plus 1 is 2. 1 plus 0 plus 1 is 2. You see it's very repetitive, this one. If I keep going. Oops, sorry. 1. Now here's the interesting bit. I carry the 1. And in any normal maths, I put a 1 up here. But unfortunately, this is a computer system, which means that is a fixed circuit. There are 8 bits in our word space, which means that anything that goes over doesn't exist, disappears into nothing. This is the overflow error. And the overflow error is something that you need to talk about if that happens. You need to identify that we've overflowed and just say something along the lines of overflow means there are not enough bits to store the answer. And you are absolutely right. What happens in an overflow error is we go from, well, not 256, but we go from 255, which is the maximum addressable, to 0. But you are right in saying that, yeah, we're trying to represent 256, but we haven't got enough bits. And that's all it is. We haven't got enough bits to do it in because it's a physical system. It's not like normal maths where we could just stick 1 in the end there. Oh dear, I forgot to mute that. Sorry if I've deafened you. Right, let's have a look at our beautiful floating point representation question, which is my favorite thing, but we do need to think about this a little bit more depth tonight. So the classic one is, in a certain computer system, real numbers, decimal numbers in other words, are stored using floating point form, using 2's complementation, a 12-bit mantissa, and a 4-bit exponent. So let's start with what that means. That means that altogether there are 16 bits storing this number. The mantissa is the left-hand side, the exponent is the right-hand side, and they're both 2's complement. Now what 2's complement means, you remember, is the most significant value is a negative. So it's the negative version of itself, which is important for you to remember when we're doing manipulation of numbers. Now, let's start by having a quick look here and doing the basic maths for that. Right, okay, sorry. Switch to that one. And what we're going to do is we're going to start off by saying, right, if I need to convert the number 16.125 into 2's complementation, the first job I've got to do is represent that in fixed point. So there's the dot. How many places do I need either side to make it work? Well, 0.125 is an eighth. So that one is a half. Then we've got a fourth. Then we've got an eighth. So that's my fractional part. That's my decimal part on the right-hand side. To do 16, let's have a look. 2, 4, 8, 16. So that's going to be that. But it's 2's complementation. So I need to go one further because that is going to be the negative version of itself. and I don't want minus 16, I want 16. So we've got here the non-normalized mantissa. Now, normalized, in the simplest way, is going to be 1 point something if it's negative, but 0.1 something if it's positive. And every question I've ever seen in this exam board has been a positive one. So we're looking to get this from this into 0.1. I'm going to do it by moving the decimal point. So let's move the decimal point until it's 0.1 something. 1, 2, 3, 4, 5. So we need to represent 5 or plus 5 in our exponent. Let's have a look how many bits it is. The question says we need a 4-bit exponent in 2's complement. That means it's a nibble. 1, 2, 4, 8, but it's 2's complementation, so that is going to be minus 8. So we need a 4 and a 1 for it to be plus 5. That means we've got, in our final version, we've got our mantissa of 0.100000001, and we've got our exponent of 0.101, but in the question, it does say that the mantissa is 12 bits. Let's see how many bits we actually used. We used 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to add 3 more bits. We add them on the end here in the gap, and they should be zeros. 1, 2, 3. Leave a bit of a space before that one, and you've got your final answer. It's reasonably straightforward to do that, but let's have a think about what a mantissa and exponent actually is. The mantissa is the representation of the decimal, and the exponent is how many points we're moving the decimal point. So what does that really mean if we're going to do a conversion the other way? Well, let's start with that same system. In that same system, there was what? A 12-bit mantissa. So let's make one up. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And let's do an exponent. And let's work out what that is. Well, first of all, we need to work out what that means. So that is going to be a 2's complement 1. So 1, 2, 4 minus 8, which means 4 plus 2 plus 1 is plus 7. That means we're moving it 7 places in this direction. Let's do it. 1, 2, 3, 4, 5, 6, 7. It's going to stop there. So we're doing 0, 1, 0, 0, 1, 0, 0, 1, point 0, 0, 0, 0. So first of all, we can see there is no fraction on this. Well, hey, this is the problem when you make them up. You sometimes make them too easy. And so that means we need to work out what this side is. So pop that into your matrix. 1, 2, 4, 8, 16, 32, 64 minus 1 to 8. Because again, it is still 2's complementation. And that is 64 plus 8 plus 1. So that is what? 73. I believe, as not a maths teacher. But that's interesting to me because what then is the maximum and minimum number we can express with that? Well, the maximum number would be this. If we've got a 12-bit mantissa, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've got a 12-bit mantissa, yeah. To express the highest number, what we do, because again, it's normalized, so it's this, yeah. But the highest number we could possibly have would be in having our mantissa set to all the ones. We turn everything on. And our exponent, to get the highest value, would again be the largest number it could be with 4, because we want to move it the furthest to the right. So as this is 2's complementation in the example we're doing, we'd want that. That's the highest number we can achieve. Now, what if our exponent was unsigned? What does unsigned means? That means it's a bog standard binary value. I won't be answering that question. Now this is this is signed here, okay? So this is not only signed, this is 2's complement signed, okay? Unsigned means that this value here, this is not minus whatever. So to get the highest value in an unsigned bit, you go boom, 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 and you put the maximum number in them. Now, what this means, I'm going to talk about this one because this is the example we're working on, but just remember that if it says unsigned, that's what your exponent looks like. Yep, this bit looks the same. What that means is this is 1, 2, 4, and minus 8. So that is 4, 6, 7. That is the most amount of space I can move this. 1, 2, 3, 4, 5, 6, 7, which puts it there. Now, that then gives us the biggest number you can express with it, and you could work that out. Well, what about the smallest number you can express with it? Well, this is reasonably straightforward as well. The mantissa is broadly the same. Now, it has to be normalized, so it has to be 0.1 something. But guess what the rest of that would be to be the smallest number? Well, this is the minimum we need to have a normalized value. And then we just go boom, 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 boom. Zeros all the way. No matter how many it is, just zeros off to infinity on the right-hand side. What's the smallest exponent? Is it all the zeros? That's what unsigned would be. How do we get the smallest exponent in a signed version in 2's complement? We've got, remember, 1, 2, 4, and minus 8. So the smallest number it could be would be this. Yeah, which means move the decimal point 8 places to the left. So we make the number even smaller. However, again, if we're dealing with unsigned values, so we're dealing with this, once again, 1, 2, 4, and 8, that's the smallest you can get. So how does that differ then? Well, the key thing is that if we're using signed values, there's a different range that we can get to. And if we're using unsigned values, there's a different range we can get to. In the same way that if we're using signed values, we can have large values that are massive, that use the entire bit, the entire byte to represent the value. We can use all zeros to represent a small value. If we're using signed values, if we're using 2's complement, or we're using bog standard signed values, in other words, sign and magnitude, then we end up in a situation where we can't represent as high or as low, but we do have that positive and negative range that we can talk about. And when you're talking about range, you're just talking about the biggest number, take away the smallest number, and how many values that can represent. And hopefully you remember that the range, when we talked about that in terms of 2's complement and sign and magnitude, 2's complement has a range of 256 values, whereas sign and magnitude has a range of 255 values, because you end up doubling up the zero. Now, what's the point then? What's the point of floating point form? Well, first of all, it's the only real way to store numbers accurately, especially very, very precise numbers. Yes. I'm just gonna pop this one up because, yeah, you are a little bit. It is comedy gold, though. It is comedy gold, and very, very big numbers and very, very small numbers that you would struggle to put inside that word space are able to be stored in floating point. The problem with floating point, though, of course, is that you have to apply processing power to work out what that number means. It's not perfectly obvious from just what it is, what that number is. So we have to do something to it to get it. If we're storing just bog standard integers, bog standard unsigned values, then there's no processing required to work out what that number means at all. You can't really store fractions and decimals very accurately if you don't use floating point. And certainly you wouldn't be able to do the sort of maths we need for sort of a perfectly rendered 3D video game if we used fixed point binary, because then our word spaces would need to be massive to represent fractional and giant numbers, which we wouldn't really want to be doing. Well, that's it from me tonight, everyone. I'll just have a quick look in the chat, see if we've got any questions about that or about tomorrow's assessment that you'd like me to answer. Of course, the written ones tomorrow is about 32 marks ish, so it's just over a half an hour. but we'll round that up to the full amount of time that you would have for that amount of questions, which would be around about 40 minutes. But aside from that, the assessment tomorrow should be reasonably straightforward maths. Please don't forget, you can use a calculator, so bring a calculator. That would be really an advantage to you. Trying to do it without a calculator, you can do it, but you know, you've got to know like your 16 times table and stuff pretty good, haven't you? So why not get that? You get your calculator, bring it in, charge it up, give it a shine, and also don't forget that most of these modern calculators, I sound like a proper old man then, most of these modern calculators will at least allow you to turn them into binary or hex mode so you can check your answers as well as you go. If you're not in on Friday, you can do it remotely if you want to do that. I have got them all set up to work remotely, the assessments. So the assessments, how they work remotely if you're not in, is they will get posted to the Google Classroom at the same time as everyone else starts that assessment. You need to be on your camera on the Google Meet for our class at that time, just in case. And what I'll do is I'll record that and ask you to share your screen as well. And you will then watch the video with everyone else, except you'll be watching it on your computer and working on the assessment. And when I ask you to stop then, during the video, you'll stop and click the hand in button to lock it at that timestamp. Of course, probably a good idea to have your sound muted, but I will be popping things down. I'll be chatting to you as you go and reminding you when times are happening and things like that. So if you do need to do it remotely, you can do that. What I would just say, though, is it probably is not going to be the best environment if you're sat somewhere in Dinas having silver service breakfast. Just saying. So try and be in the lesson if you can. But if you do want to do it remotely, that is fine. You just have to be on the Google Meets at the same time as the lesson's happening, so that I can validate your work. Right, I can't see any other questions there, but go and practice that stuff, please. Particularly, do practice the thing that I sucked at tonight, which was the boolean simplification. It is reasonably straightforward, he says, having got it wrong, but it does take practice, and you do want to be quite awake for that part of the assessment. In fact, why not start it off and get cracking with it? Okay. Right. Sorry, another question. Can I use the same login that you use in school? Yes, it will have to be. It will have to be your school login to log into the Google Classroom to make sure that's all validated and all that's working. Right. Thank you very much, everyone. Have a cracking evening. I'm sure you all have a great time revising this. I'll see you tomorrow to do the assessment. And don't forget that what's going to happen is tomorrow night at 9 o'clock, we're going to go through the next few topics. Right. Night, then, everyone. Toodaloo.